Morning, everyone. So our first speaker is Amaury Hayat from École de Ponts, and he will talk about AI and pure mathematics. No. How artificial intelligence helps mathematics? I'm sorry.
Thank you very much. I'd like to thank the organizers for the invitation. It's a great pleasure to be in Miami today. It's also an honor and I must say a bit of a pressure to be giving this talk right before the talk of 20 hours and after the amazing talks of yesterday. So my name is my name is Amaury Hayat. I'm a professor at École de ParisTech, and I often get the question, what is École de ParisTech? So I thought I would just add one slide about that. École de Ponts is actually one of the top universities for science in Paris, but it's also a very small university. We have like 200 undergraduates per year in total, and 40 of them every year happen to choose mathematics as a major, so it's relatively small. I explain why you presumably have never heard about it before, but I'm sure you've heard about some of our former students. Joke aside, I'll start this off by saying that we are all using AI tools, and we've all been using AI tools for many years now. Most of the time, without even realizing it, these are the easiest examples. But something changed a year and a half ago, and what changed is, I see that I'm not on the camera, so I'll move a little bit. What changed is that large language models were made available to the general public. So the technologies didn't change that much, but what changed was the awareness of the public about the impact of AI. So it was an awareness of the general public, but also an awareness of scientists who started realizing that these kind of tools will be useful in their field. And I think this is a little bit the reason why we are here today. So today I'm going to try to convince you that AI is actually already useful in mathematics and that it has its place in the future of mathematics, even if I'm cheating a little bit, because given yesterday's conversation, I feel like everyone's already convinced. But I will do it anyway. So my talk will be in two parts. First, can we use AI today in mathematics? And I'll try to illustrate this on a few examples. And on the longer term, can AI try to prove theorems, or at least steps of the theorem? So I'll start with the first part, and I'll start by saying that, as surprising as it may seem, we've been using calculators to prove theorems for a long time. My favorite example is this one. It's a conjecture by Euler of 1769, so of course they didn't have a calculator at the time. What Euler felt was that if there exist integers a1 to ak and b, such that if you put the k first to the power n is equal to the last one to the power n, then k is larger than n. And he wasn't able to either prove or disprove this during his life. And actually, no mathematician was able to prove or disprove this for almost 200 years. This was until Wiener and Parkin arrived in 1966. And they solved the question in the most silly way you can think of. They just tried all the possible combinations, first possible combinations with a calculator, and they essentially got this. So you see that you have 4 integers here. So according to Euler's conjecture, you need to have 4 that is larger than the power, which is 5, and so we all know that this doesn't work. So this was a new mathematical result, but most importantly, it was also the only math paper I know of that can only fit on one slide. All right, so in a more recent example, there was the proof of the Keller's conjecture. What these researchers managed to do is to reduce the proof to checking many simple cases. And but the thing is, these simple cases, there are really too many for a human, far too many. To the point that when you're asking how big is the proof, you're not asking how many pages, you're asking the weight of the proof. And it's actually 200 gigabytes, so it's about 10 times Wikipedia. So if we were to read it out loud during this talk, I mean, we'll be there until next year. I don't know if there will be a next edition. So the conclusion is that computers have been used to prove theorems for a long time. The only thing is that usually they were used to have a simple case checking with a lot of cases. So what the question that I'd like to investigate more here is, can we use AI to solve more complicated problems and to be more useful than what is already very useful, is checking the high number of cases? And I'll try to convince you that the answer is yes, based on 3 examples coming from different areas of mathematics. The first one will be dynamical systems, stability of dynamical systems, the second one control theory, and the last one in topology. So let's start with the first one, and we're going to consider an ODE, so x prime is equal to f of x. So I don't need to convince you that this can model really many things. Well, I'm trying to do this as a very general public talk, but really, that's the point there. So essentially, you can do a lot of things with these ODEs. We do just a few general assumptions, but you have n ODEs. 0 is an equilibrium, so f of 0 is equal to 0. And the question you'd like to know is whether this equilibrium is stable. What does this mean? It means that for every epsilon, there exists a delta such that if the initial condition is smaller in norm than delta, then the solution exists for any time, and the solution is smaller in norm than epsilon. So, in other words, are all solutions arbitrarily bounded if the initial condition is sufficiently small? If I make a drawing, it's like this. Can I make sure that for any red ball, there is a blue ball such that if I start in the blue ball, I don't know what the solution is going to do. I don't pretend that I know this, but I know it will never go out of the red ball, right? So this is a projection in 2D of a 3D curve, because otherwise you don't have the crossing, but this is essentially the principle. And so this is a problem that has been studied by mathematicians for a long time. You can think of the work of Poincaré with the three-body problem. So it has interested mathematicians for over 100 years, and thanks to Liu Xin and Netflix, it has also interested the general public for about 3 weeks. So on this problem, one of the main advancements were what we call the Lyapunov functions. So what Lyapunov said is that if there exists a function such that it's strictly minimum in 0 in the equilibrium, it goes to infinity at infinity, and you have this squared condition between the gradient of the function and the dynamic of the system. Well, if you have this, then essentially your system is stable, the origin is stable. And so it's a very powerful result because it reduces the question of stability, which is a very complicated question to answer, to the existence of a Lyapunov function. There's just one tiny little detail, which is that this theorem doesn't tell you at all how to choose a Lyapunov function. How are you going to find one? And in fact, it's not that much of a detail. It's not a simple problem. For instance, if I give you this system and I ask you, okay, is this system stable? I mean, you can try to look at the linear system. It won't give you any information because the linear system is essentially x prime is equal to 0. And so it's not completely clear. I mean, it's not that easy to see that this system is stable, and there is in fact a Lyapunov function, which is this one. And believe me or not, but this is actually a very simple example because the Lyapunov function is not diagonal. So even the simple examples are already a little bit important. In fact, it's such a hard question that today it's perfectly legit to do a good paper that says this type of system or this type of system is either has this kind of Lyapunov function or not. So today, more than 100 years later, it's still an open question. There's still no systematic way to construct a Lyapunov function, and we actually don't know if there is one. So what do we do, mathematicians, when there is no systematic way to prove, to find a result? Well, we resort to intuition, and we're very happy, usually, because it means that we have something to show. Intuition is an important concept in mathematics, and in many cases, it resembles a kind of pattern matching. In the sense that you've seen plenty of examples, this gives you an idea of how to proceed in a case you've never seen. And because we know that neural networks are good at pattern matching, the natural question is, can we train an AI to have better mathematical intuition than us on specific problems? And so this is what we tried, trying to guess Lyapunov functions, so an AI that guess Lyapunov functions. So again, the problem is this one. I give the AI system, and I'd like that the answer is yes, and this is a Lyapunov function. So of course, I don't know what's happening in the middle because it's a black box, but checking that the function is a Lyapunov function is not always simple, but it's much more simple than actually getting a candidate, right? If I have a candidate solution, it's easier to see whether it's actually a solution, so I can check. So this is what we did with Alberto Alparno and François Charton from MetaAI. And so there was a preliminary paper in 2023. This is a full paper is in 2024. It's not yet in archive, but it will be soon. And what we use is a transformer architecture. So it's essentially the one that we've already discussed yesterday. It's what there is in ChatGPT. It's just 1,000 times smaller. It's not autoregressive or so. And the procedure is the following. The first step, and this is really the crucial step, is to generate a set of systems and associated Lyapunov functions. You want to be able to train your neural network, so you want to have a set of examples with problems and solutions. So this is really a crucial step. Why? Because there starts one of the main questions. How do you generate 1 million examples of problems and solutions for a problem that you don't know how to solve, right? So of course you can focus on particular cases that you know how to solve, but then you bias your distribution up to a point that the AI will probably only guess what you train it to guess. So one way of doing is to use a backward approach. Instead of finding a solution from the problem, you start by sampling the solution and you construct the problem from the solution. So in this particular case, assume that you can have a mathematical way to get a function that is positive and random. This is actually not very easy at all, and in fact, we can't generate at random any positive function. You can essentially generate sum of squares. You can use things like exponential is always positive or real numbers, but it's actually already a complicated question. And then you have to find a mathematical way from this to find all the systems with this definite function, and then you sample. You have generators that sample there. So in spirit, the way the backward approach works is the fact that finding the definite function is a hard problem, but checking that the function is the definite function is easier. So you're trying to leverage.
What you need for a PKC, that's what you need for public key cryptography, something that one
Exactly.
way is very hard and one way is very easy.
Exactly. Completely. And in fact, they're with the same architecture. One of my co-authors, François Charton, tried to attack public keys the same way, and it did something. So
and is it a distribution over the coefficients?
sorry.
So is it a distribution over the coefficients of the?
So you try to sample at random, like of course the coefficients, but also the functions. Like you're saying, okay, I'm allowed to these kind of functions. So I'm sampling the operators at random. So we'll see in a minute what does it mean to sample the mathematical expression at random.
Okay.
The only thing I'd like to say before this is that even with a perfect generator, assume that you can do this. Like, okay, I think it's not really possible, but assume that you can sample any positive function and create any definite function with it. Even then, it will still bias the distribution because you are essentially biasing it towards a complicated expression because you're starting from the solution and building from there. So you essentially have less simplifications than the other way around. So and it does matter when you're training the AI. So it is why I'm saying all this is a crucial step. The second part is encoding the example, and this is how we're going to be able to sample at random. What we're doing is we're taking mathematical expression, we represent it as a tree, and then there are tools, there are many tools in fact to sample trees at random, tree structures at random, and then once you have the structure, you just sample the operators at random and then the leaves at random. And then we enumerate the tree in a given order, that's always the same, for instance, top to down and from the left. So here if you do this, you get plus, power, 1, 2, sine, x2, which is exactly here. And so this is the way we represent the mathematical expression into a tokenized sequence. So this is our tokenization. This is what we feed the transformer, the neural network with. And then at the end of the day, we train the language model. This is the classical part, so I won't detail it. I'll go directly to the results. And the first thing that you can observe is that if you're doing this, it works. It works. The AI learns the mathematical intuition of definite functions. It's most of the time what it gives is not correct, but what it gives is correct. A really non-negligible amount of time, which is already a lot. But you can do better than that. Surprisingly, if you add a few high-quality examples, so examples that you will generate in another way, maybe much more costly computationally speaking, so you can't generate a full data set with this, but like high-quality examples to the training set, then it starts to work exceptionally. Even if you add only, in fact, 50 examples out of 1 million, which is nearly nothing, it starts to work perfectly. And my understanding of this is that it essentially changes the length of the average length of the system, and this matters a lot for a transformer architecture. So what you get at the end of the day is something like this. You have for polynomial systems that have a sum of square definite functions, you have algorithmic way of trying to find definite functions. They are represented here, so you see they're not perfect, but they give you not so bad accuracy. But that doesn't work when you are looking at non-polynomial systems. The AI, however, is working very well most of the time. You see, it gives an accuracy that is always higher than 80%, and this is huge. Why I'm saying it's huge is because when I try to give these kind of problems to my master students, I get an accuracy of around 10%. This doesn't seem much, but in fact I tried with myself, and I got an accuracy of 20%, which is not that much either. So really, we now have an AI that is able to guess solutions to the problem that is much better than what we were able to do before. Remember, I showed you earlier a paper of 2011 that was finding the Lyapunov function for a class of systems. So we tried to put this class of system to the AI, and the AI outputted an equivalent solution to the problem in like a few milliseconds. No, a few seconds. Yes?
Are you taking then the ones that are generated and adding those to the data pool for training?
So so it's a very good question. What is essentially what are we testing on and what are we? So you're saying if we generate?
Well, you said that you use this backwards process to generate.
Yeah, this is our
systems and Lyapunov functions.
Yeah.
But now you're using it to find some.
Yes.
You input a system and you find a Lyapunov function.
Yeah.
Couldn't you add those examples to the training?
Yeah, I see another question. Yes. We could definitely do this. We haven't been doing this because it takes some time to generate an answer. And actually, it takes some time to generate an answer, but it takes more time to check the answer because when the Lyapunov function outputs an answer, you have no guarantee it's correct. You need to check it. So either it's a polynomial and you can check whether it's at least somewhat square or something like this, or it's not, and then you have to check by hand, or the very least is you have to do some numerical simulation to see that it's kind of reasonable at least, and this takes some time. So then having something that could add a lot to the training set would take some time. Although, as we're saying here, even a few high quality examples help. So maybe it will help still and we haven't done it, to have just 1,000 examples. Okay, so
I'm sorry.
Yes.
Yeah, but that's thank you. That this is super exciting and interesting. That's a great point, obviously, because if you get all these answers from the system, you don't need to check and validate. I understand why you're not feeding that to the training system because you don't know if they're hallucinations for the transformer or if it's reality, right?
Or it takes some time to
time.
check.
So you need to manually validate that each one. If you're going to feed them as training data, you will need to manually validate that's correct, right?
Yes, correct. Although I would trust some good numerical simulations, but that still takes a lot of time.
Yeah, exactly.
Essentially, because Meta was very generous with the computing power, as soon as it gets below 1 second of generation for one example, we're fine, but above that, it starts to be really hard to try.
So like with regards to this topic, like if you take like the SAT problem, that's NPR, the check for correctness for dynamical systems, can you speak more to, I'm not an expert in this area, like how quickly is that from like a process standpoint?
The check of correctness?
Yeah.
The thing is, the check of correctness, we have no automatic way, we have no perfect automatic way of doing the check of correctness.
But even if you had like a heuristic situation, I can imagine you setting up a pipeline where you do some kind of dynamic, I don't know what it would be, but like, I imagine you can make an automatic pipeline for that. Like, would that just be like hard from like a computational standpoint? Or would you have to get like experts to say, these XYZ processes are good enough for us to say that this is a likely.
So you could have something, you could have an automatic process that gives you at least good confidence that the solution is correct, which is what we use when we're not manually checking. But this will take, I think, at the very least, a good 10 seconds per example, but at the very least, and sometimes more. And this starts to be a lot when you want to add 1 million examples. Of course, for 1,000 examples, it's fine. For 1 million examples, it will take some time.
Yeah, and I'm sorry. And I think this is, I'm not a mathematician, I'm an engineer. So from my perspective, we have built hundreds of AI systems. This is the real challenge at the implementation side, which is, that's why when we use transformers or any algorithm to find patterns and guess possibilities, the challenge is that if you don't have the data at the end of the day that validates what you just generated from your AI system, then as a system it's not really useful.
Yes,
right?
yes, completely. That's why we wanted to output the Lyapunov function so that we can check. The only problem is that this is very good for checking, but then to use in the training set, we will be able to use it as a small fraction of the training set. But then we can't really do much more than that because it takes some time. Even 10 seconds is too much.
So the input data, like the actual structure of the equations, are you trying to diversify the number of or sort of the structures as much as possible.
Yes.
Yeah, okay.
As much as possible with a range of, so we usually have a range of number of equations though, to avoid, so like 2 to 5, 2 to 3, 3 to 7, to have a maximal and range of the length. But it could go from small equations to like nasty equations that would take one page to write.
That actually kills it as a PKC.
Sorry?
This result kills it as a PKC for polynomial. I mean, maybe if you do non-polynomial, but 87% also.
Yeah, no.
It's not a good PKC because of this result.
Right, but then.
No, I'm just
Yeah,
mentioning
right. But then we need to
improve it.
Yeah, the tremendous and incredible value add, right, is that instead of testing all these million of possibilities, now with this outcome, you have a subset to test that.
Yeah.
It's a pretty significant.
Yeah, the goal is to say, the goal is to say, let's try this.
That's
If
right.
it works, great. If it doesn't work, then you're going back manually to try to do something.
Absolutely. So it drastically optimizes your processes and improves your possibility of success, which is.
We hope so at
Yeah.
least. But to be fair, I mean, we're really not very good in this problem as humans, just because it's quite complicated. I also think that as a SAT, just like for the SAT problem, there's no way that we can solve it at 100%. You can solve an NPR problem at 100%. We know that for Lyapunov functions there are several problems where the problem is so sensitive that it's unlikely that you'll find anything with this. But we hope that maybe 98% is still possible.
So what is your definition of diversifying you just, instead of the second power, it's the sixth power instead of.
Yeah, there's a sine, cosine, so essentially it doesn't know the functions, you're specifying its functions, and you need to be able to specify the gradient of the function of the differential of the function. But everything is text for the neural network, so you could define whatever function you want tomorrow and say that the gradient is this, you could add it to the functions. We're restricted to, I don't know, sine, cosine, tangent, x, logarithm, square root, or and for polynomials, I think we had the power up to 12, or depends on same for the coefficients, you don't have to be too much.
The answer, the Lyapunov functions are the same sort of function? How do they specify it?
Sorry?
Is the answer, the Lyapunov function that the system finds, is it also written in terms of the same operator?
Yes. Yes.
So just a very quick question. So if I understood correctly, if you are to add something to your training set, you would want high quality examples. So the solutions that you get, I mean, are kind of the same way. Are they high quality? Would they be worth, like, most of them, would they be worth having? Or I'm sorry, this is like.
It's not that much. What in fact the high quality data, I think it's more about the system than the solution. So I would say the answer is yes. Here, that's why we have two different distributions. This one is more like the problems you will find in real life. It is expensive to generate, and this one is the training distribution, so it's the backward one that's less natural. So if we find solutions to this one, we could add it to the training set, because then that will be what we call high quality data. The way we generate the high quality data right now is very silly. We're generating a system at random, purely forward way. We try to see for polynomials if there is a sum of square Lyapunov function with the costly algorithm. If not, we throw it away, and we throw it away so 99% of the time, because there are very few stable systems. And we do this again until we have enough examples. It takes you a night to generate 1,000 examples. So that's why we're not using it for training. All right, so my second example that we quicker will be on control theory. So we're going to dive in the applied mathematics now, because we're going to look at a system that models the population of mosquitoes. So you have the eggs, the male, the female, the sterile male. And what you can do in this system, you have a way to act on the system. This is why it's in control theory. There's something you can change the system. It's the U here, which means that you can add sterile mosquitoes. And the hope is that the female cannot discriminate between male and sterile mosquitoes and sterile male, and they can't reproduce with them. So then it will drive, hopefully, the population of mosquitoes to zero. this is something that I've heard to be useful in Florida. So, for example, so this is what we call the control. And here, because it's a physical problem, you can't choose really as you want. You can't measure everything. What you can do is measure the total number of male and the total number of females. So the female and fecundated female and the others. So you'd like to choose, from a mathematical point of view, you'd like to choose U as a function of those two variables. And your problem is the following. Is it possible to find U as a function of those two variables such that, so not only the system is stable, now you know what it means, but the eggs, the male and the female goes to 0, the population of them goes to 0, and the population of still male goes to epsilon. It's a classical mathematician result. We want to make it possible with epsilon as small as desired, and F will obviously depend on epsilon. As small as desired, I think we stop at 10 minus 5 mosquitoes. Right, so this was an open question, and a question that actually some mathematicians brought to us because they weren't able to solve this. And we thought, okay, we're unable to solve this. Can we use an AI to help us solving the question? Same as before, we want to use the AI to give us an intuition, and then we'll check that it's actually a solution. So we used a reinforcement learning approach, and the way it works is the following. First, you transform the equation using a well-chosen numerical scheme. So you discretize them with a well-chosen numerical scheme. I'm hiding everything in the well-chosen. And then you train the reinforcement algorithm model. So the AI that will train by trials and error and try to maximize a well-chosen objective. Here again, I'm hiding everything in the well-chosen objective. And then at the end of the day, if it works, you get something that is a black box numerical control. So it's not a mathematical solution. It's a numerical black box. You give it an input, it gives you an output. And then starts the job of the mathematician. You try to deduce what this black box looks like as a mathematical control from the numerical control, and then you want to verify that this is a solution of the problem. Of course, this can only work if there is some kind of regularity in your problem, in the sense that if you have a solution, perturbating it a little bit will still remain a solution, otherwise a control solution. Otherwise, from the numerical control, there's no way you'll get the mathematical control back. So this is what we did, and with this mosquitoes problem, you see this is so it learned, the AI trains, and this is a numerical solution it gives you at the end of the day. So I told you this is a function of two variables, so you have here m plus ms, so total males, here f plus fs. And the only problem is that, I don't know for you, but me, when I look at this plot, I have no idea what will be the functions behind. Fortunately, I have a very good PhD student, when he looks at this, it says directly, you need to look at it in log-log scale, it will be better. And in fact, it's indeed better in log-log scale. So you see that there are essentially two areas. One where you're not doing it, when you're at max value, so you're adding zero mosquitoes at most as the maximum capacity for the factories, and another one where you actually have you're doing nearly nothing. So you can translate this in mathematics. It gives a complicated formula, but there starts the work of the mathematician to understand what's the important part of it, and actually the important part of it seems to be only this. So this is a form of control that I will never have guessed because of this log here and the switch. But what's interesting is that it works. If you try this, it seems to work, let's say. We haven't completely finished the rigorous proof. So it seems to work. And it seems to work for any epsilon larger than 0. And what's very nice is that now if you try to have epsilon is equal 0, it will not work. You have some kind of oscillations, dense oscillations, but still. And so it's very nice that with something as approximative as neural networks, you can see this kind of duplication. Yes.
Yeah, Amaury, so this is great, incredible. Question: this derived function formula, the control, it's based directly. It correlates to the data because of the weights, right?
Yes.
So, would you say that it's valid as long as the data that you feed the network it's similar to the original data? And at what point do you think your I guess from a percentage perspective, your control or formula or equation won't be valid based on different, because data is always biased.
Yes.
When we have infinite data and we automatically take a subset of data
Of course.
to feed a model, it's already biased.
So I think if you're, so the data are just the simulations from the system, the original system. I think if you're taking the exact same system and try with any initial condition, it will work. I mean, we've really tried very far. The legit question is, it's a real problem. What happens if the coefficients are not exactly the same in the system, in applied mathematics? And this is exactly what the reviewer asked us. And so the question of the robustness of the solution. And the solution still works if you had some uncertainties essentially everywhere on the parameters. And the answer is yes. You can actually have a relatively wide range. I mean, you have a factor of 3 essentially between the minimum and maximum, and it will still work. Which leads us to believe that we cannot have a meaningful solution somewhere if it means anything. All right, so my last example would be topology. I'll be very quick because I can't compete with the expertise of the people in this room. I'll just say that I'll just recall an article that you probably heard before. It's an article from the team of Georgie Williamson and the team at DeepMind that was published in Nature in 2021. And the abstract principle is essentially the following: you have mathematical object Z, and you have quantities X of Z and Y of Z that you can define, and you'd like to know whether there's a link between the two of them. So what you're doing is try to train a neural network to predict one from the other, and then if it works, if it trains, it means that there is some kind of relationship that we just don't know. But then you have your neural network that is an approximation of the function linking one to the other, and you can try to attack the neural network and understand what there is in these black holes. So in this, they found the link, they conjectured the link between hyperbolic and algebraic invariance of nodes. Obviously, I'm very far from knowing as much as the experts in this room about nodes, so if you have any questions, you can ask them. All right, so I hope I convinced you that AI tools can already be useful in the practice of mathematics, at least in these areas, and help solve difficult problems. And essentially, what we're doing here is training the AI to have an augmented intuition, and this augmented intuition allows us to bypass the difficulty of the problem. Now, in all these examples, though, where the AI is not outputting any proof steps or any reasoning or anything like this, the human is behind. And the question we could ask is, can an AI prove a mathematical result on its own, or at least, even a small thing with some proof steps? And this is the second part of the talk. And if I were to ask you, okay, you need to give me an AI that can give a proof of a mathematical statement, what is the first thing you will probably try to do? I guess you will probably try to train your own GPT model. Oh yeah, I plan to say that there are essentially two questions. Can an AI find a proof for a mathematical statement? And this is the one I'm going to look at today. There are many people looking at it. There's a related question: can we automate human reasoning? This is not the question it's not exactly the same question, not the question I'm looking at here. But there's a research group led by Timothy Gowers in Cambridge, so I'm already assuming that you'll stay for the next talk, but we never know. So yes, I think the first thing you can try is to train a GPT model, and there are some people who actually did this in 2020, Stanislas Paulu and Ilya Sutskever. So Ilya Sutskever, this one, used to be the chief scientist of OpenAI. He's remembered by the general public for being the man who fired Sandman. Well, it's a shame because he should be remembered for being really an amazing scientist. I mean, he's relatively young, and of course you can't compare the citations in math with machine learning, that is a super trendy area. But still, I mean, even in machine learning, he has a profile that is impressive. So just let's go back to so they did this, and they trained their own GPT model. And I think to understand what's followed, I think it's good to have a small reminder of how works a GPT model, how works the autoregressive transformer, just in a nutshell. Of course, I'm forgetting a big part of it. French people like to put French things everywhere, so it's going to be in French. So if you have a sentence and you would like to complete a sentence, let's say, well, you start with something. Then what the neural network is going to do is look at the sentence, compute the density of probability thanks to the training that corresponds to the sentence, and then sample a word. Here, either you speak French or you believe me if I tell you that the most likely word is probably il after this because of this here. And then the autoregressive part is to put it back again in the sentence and do this again, right? And this is actually a sentence from a French book called La Comédie humaine d'Amaury. So because it's on the internet, if you train it on the internet, it's highly likely that you'll get this sentence. And at the end of the day, something will say, I sample an end token that will be, for instance, a full stop or a question mark, and it's going to say, okay, this is the end of your sentence. So this is the way it's going to work. And you could think of doing the same with a math statement, right? So now you're having a math statement in input. You have your statement. Because you've trained the model, it computes the density of probability of the next step with respect to this statement, thanks to the training. Then it will sample a step. Then autoregressive part, you're putting it back in the sequence. Then you compute again the density of the next step, and so on. And you hope that at the end of the day, if it works, the neural network will look at this and then will sample, this is the end of the proof, and then if it works, you just take the right column and this is your proof. So this is maybe the naive way of looking at it. If you're working in a formal language with a computer assistant, you can actually do a bit better than this, because you can at each time compute what happens if you apply the step that you just sampled. So you have your statement, compute the probability, sample the first step, then you apply the first step. In the computer assistant, this gives you a new state of proof. So you have this state of proof, you sample the next step, and so on. And at the end of the day, you hope that you have nothing left to prove in the computer assistant. If you have nothing left to prove, you mean that you prove the theorem. And then you don't even need a neural network, you just say, okay, this is the end of the proof. You take the right column, it's your proof. So we can be skeptical about the fact that it's going to work, because you're only looking at the next step, so you have no global vision. But on the other hand, you can also think that ChatGPT is doing exactly the same with like if you ask an essay on something, and it does give relatively good essays. Whether you are skeptical about it or optimistic about it, this can only work if you have enough examples, right? And when I say enough, I mean enough sufficiently diverse and sufficiently numerous. So you need really both of them to get something that might start to be good. And this is a problem in this area, because there is very few data available, especially if you're looking at formal data. So there are two types of language that you can use. The informal language, so essentially you can write a proof in French, English, Chinese, whatever you want, but it won't be computed through formal and checked by a formal assistant, so you can miss some steps or just skip a little bit of it. This is what we're doing. And you have formal language where everything has to be specified, and you need to specify all the steps, and at the end of the day you get a guarantee that the proof is either correct or that you haven't proved anything yet. The good point of working in a formal language is that the AI cannot really fool you. It outputs something, and the computer assistant tells you whether it works or not, but there is no in-between. In informal language, my belief is that at some point it will be easier for an AI to fool a human reviewer than to actually prove the theorem behind. That's my own belief. The problem is that in formal language you don't have that many theorems. In mean, you had the order of magnitude, I think, is 100,000 theorems. Now it might be twice as this, but this is large data sets of theorems for humans. Of course, I'll never know them by heart myself, but it's a very small data set for an AI. And so if you want to know more about what you can do in this situation, so this is the limit of the approach. If you want to know more about what you can do, there's a nice paper by Fabian Glöckle of 2023. It's 4 pages or 6 pages, I think it's relatively small. But what is the best you can do in this constrained area, and you can and can't do? So the second approach, that's the one we worked on for 2 years and a half with Guillaume Lampe, Marine Lachaud, Thibault Labrie, Gabriel Martinet, Gabriel Nervo, Aurélien Rodriguez, and Timothée Lacroix in 2022, is to treat mathematics as a game, right? In the way AlphaZero or AlphaGo was doing before AlphaZero. So why? Well, because DeepMind in 2017, as we've already heard, released a reinforcement learning model that was able to learn chess on its own and to play chess against itself and then become the best player of all time and better than any humans. So we thought, okay, let's do this with mathematics, where we're taking this as a game. So the game is this one, you have a statement. Making a move is applying the theorem. So you apply the theorem, now you have assumptions to satisfy. So you have to show the assumptions, and again, you're making a move, this is done. This, you're making a move, then you have 2 assumptions to satisfy. You're making a move, it's done. You're making a move, it's done. And then at the end of the day, if you have nothing to prove, then it means you won. So this is the fun game we're all playing and that we wanted the AI to solve. And but there are many difficulties. The main ones are the following. The first one is really an AI difficulty. Having a two-player game versus a solo game is a very different game. If you have a two-player game, you can have many clones of the AI that are playing chess against themselves, so one against the other. At the end of the day, even if they are all very, very bad, one is likely to win. And so you have some feedback. You know that this way of playing is better than this way of playing. Now, assume that you have a solo game like math. You give an exercise. It might be very easy, but all your AIs are extremely bad. They all try to prove something. They don't manage to prove anything, and then at the end of the day, well, you don't get any feedback. So it's really a high limitation. The second one is that in chess, when you make a move, you always have a single game. Like you move the bishop, then you still have just one chess ball. In math, you apply a theorem. Now you have to satisfy the assumptions. So if you're doing something in a completely uncontrolled way, the number of things you need to show might increase exponentially quickly, and you might saturate in memory just even before knowing whether it's possible or not. But not the point. It's really a math part. This one. It's hard in mathematics to know automatically in the middle of a proof what is your probability of succeeding. I mean, except if you already you can say most of the main steps are gone. So now I think I'm going to succeed. This is fine, but if you're really before this part, saying, okay, I have 30% chance of succeeding is usually a complicated task. It's even more complicated to say it automatically. Like I'm giving you a statement in the beginning of a proof. Can you derive an automatic way of telling me, okay, this is the probability I have to succeed? In chess, at least you have some kind of proxy for this. Even if they are bad, they are still giving some information. And the last thing is that the number of possibilities is much larger in mathematics, of course. I mean, if you have a mathematical statement in front of you, the number of things you can do is not unlimited, but close. I mean, you could introduce a new assumption that could be many different things. So it's not like in chess where the number of possible moves is essentially of the order of 100. All this to prepare you that to the fact that we haven't managed to train an AI that's better than any human, and I think that's for the best. So it's much more difficult than chess. And the way we've been doing this is the following. We have two transformers now, one that predicts the next step, and the second one that will predict how hard it is to prove some kind of statement. The reason for this is the following. I can give a very brief explanation in a few minutes. Here, if you have something where you have a neural network, so you have the statement, and you have a neural network that will tell you, okay, this is the step that you should likely do. Well, you can just go like this, or you could say, okay, maybe I can sample several different steps. And I can see what happens if I apply these steps. So for the step A, I will have to show assumption 1, assumption 2. For this one, maybe I just have this one. And for this one, I might have something like maybe H1, H4. And then you can have your second model that tells you how hard is it to prove these. And if it tells you that H2 is essentially nearly impossible to show, then it means that you might consider doing something else than the step A. You might consider doing another of them. So we were essentially doing something like this in a slightly more advanced way, but essentially kind of this principle to do a kind of a proof search to see what will be the next step. So I won't say it much because I think I'm close to out of time. And then essentially what you hope is that you are proving things. So you have some successful examples and some failure. And this will help you train those two models, the transformer that predicts the next step and the transformer that actually predicts the probability of success. So with this, what happens? You end up with an AI that is able to prove some exercise that, let's say, at the graduate levels, they have good accuracies that on middle school and high school exercise that you really up to Olympiads level in high school. And they also are able to prove a few exercises from the International Mathematical Olympiads. For instance, this one shows that for all n, 7 never divides 2 to the power n plus 1. So that's a good exercise. You can try to do it, and otherwise I can give you the AI proof. This this was a paper of 2022, and it was the state of the art on this high school exercise. It was the state of the art on this high school exercise until, or little exercise, until 2 months ago, I think. So it lasted a year and a half in an area where things change every 3 months, so we're relatively happy. It was done before there was ChatGPT and any large language model. The model behind is, I think, 500 to 700 million parameters, which is a lot, but nothing compared to the current models.
Are they developing their own model, or are they using one from one of the
UMass or the new state of the art?
what is your team?
Oh, my team, yes. We developed it from scratch, which will be a terrible idea to do. I mean, it will be a terrible idea to do this today, because today you have access to pre-trained models that are, the fact that they are pre-trained helps, in fact. We realized here that if you train it a little bit on English first, it was helping after, just because you waste, when you're training, you're wasting the first few, the first data just to go from a white noise to something a little bit more organized. So today, if you were to redo this again, we would probably go back from a pre-trained model, but at the time there were no pre-trained models, it was a open source, so we started from scratch, 500 million parameters. Yeah.
But do you have a way of taking a pre-trained model and modifying the architecture, but still inputting the parameters that were in the pre-trained model to some part of the architecture?
That's a good question. That's a good question, and I'm afraid I'll say something wrong. We are not changing the architecture anyway, because we're using some pre-trained models that are, we're essentially using small pre-trained models that are still LLMs, and then we put the LLMs in the larger proof search with the reinforcement learning loop. But we are using as a single brick the LLM that we don't change, except that we are retraining, we are fine-tuning it, of course.
Right. I'm sorry. So you're not taking, to simplify, you're not taking the transformer paper from Google or from 2017 and coding your own transformer. You're taking a pre-trained model, but then putting your data and continue to train.
No, so that will be what I will do if I were to start this today again.
Yeah.
But at the time, we went back from rewriting our transformer, our own
You were
autoregressive
writing your
transformer.
transformer.
Yes, but because at the time,
Okay.
there weren't these pre-trained models. So
If you take a pre-trained transformer,
Yeah.
You can always feed it new data and it will focus on that. But I don't think you can change the architecture, right?
no, then
You can't change the architecture of a pre-trained model, but you can definitely rewrite it.
Well, you might be able to take a new model that has like less parameters and just sort of copy the weights into the new
You can do
parameter.
that,
Take a subset, copy them, and see what
Yeah,
happens.
the
I mean,
weights for
you're just
sure.
asking for something that has some kind of order that you don't really care about. So
no, that will be a nice thing to try. I mean, yeah. One interesting thing is that, we were a lot of people for a lot of time. I think I've never spent as much time on this paper, than on this paper, and there were at least 4 people who spent more time than me. What's interesting is that these 2 people, Guillaume Blanc and Timothée Lacroix, after doing this paper, they realized that we had a new language model that was very good, and so they founded their own startup that is now called Mistral AI. So now they raised in 1 year they raised $1 billion, and now the startup is worth $6 billion. So it all started by doing AI for mathematics. So I don't know if there is a better motivation.
That's amazing. Okay, so I understand now. You did write your own transformer, and that went into Mistral. That's
So first it became Llama, because our
that's
team was the Évariste team at Meta. It was merged into the Llama team.
Yeah.
And then after Llama, they went to Mistral. So yes, that answers the question.
Yeah, that answers my question. You wrote, Yeah.
But today today we would definitely take one
Yeah.
of the open source one. All right, so this is the end of my talk. Essentially, so I think the perspectives are the following. It will still help a lot. I mean, all these approximations of human reasonings are extremely bad. I think it will help a lot to have approximations of human reasoning, at least on the short term. It will be also better, I think, to have more organized reasoning with a hierarchy of tasks. If you're looking at these models right now, applying A plus B is equal to B plus A is of the same importance as applying, I don't know, dominated convergence. One is probably more important than the other one, or at least not as frequent. And so you might want to have a hierarchy of tasks and the foresight of intermediate tasks. And one important thing will be to obtain more formal data through self-formalization or auto-formalization. So you will essentially want to go from a math proof in informal language written by humans, and then you would like to transform it in something that is formal. So you will have, of course, you are missing steps in informal language, but you will hope that some kind of proofs like this will fill in the gaps. There were several works about that, and there's recently a project led by Fabian who just started. Fabian is a very bright PhD student, so I think it's a name that we should save for the future. Then
Self-formalization different from auto-formalization?
no, it's the same thing. It's just me translating. You're just waiting for the community to converge to something. It converges since 2 years to auto-formalization, but I was using self-formalization before, so and I left it on the same.
So you're implicitly using the Curry-Howard isomorphism concept to do this.
Yes.
This notion.
Yes, but in fact, when you're starting from informal language, you really don't have an isomorphism to the informal language. So because you're missing a lot of things. So the problem, I think, is really messy. And right now, we're not even able to. We hope that soon we will be able to formalize that the community, not us. I mean, the community will be able to formalize like math textbooks and so on. But the real deal will be like, is anyone able to formalize archive one day? And this is hard. I mean, you know, archive proofs. Sometimes the assumptions are not in the theorems; they are like 3 pages before. But a human will definitely know what happens of the same field. I would say, yeah, definitely. Maybe, right. So maybe you only look at the papers where humans know what happens. But at least the machine, it will be extremely hard for the machine, and I don't think we have anything today that is close or even remotely close for even being able to do this. Right before concluding, I do shameless advertising for a workshop that I had a chance to co-organize in ICML, so in Wien in a month. It's interesting because it's the AI for Math workshop, but ICML is actually it's an AI conference. It's one of the 3 main AI conferences, and so it shows you what the computer science community, where is the computer science community, what's the state of the interest of the computer science community in the field. So I hope I convinced you that AI methods are already useful in the practice of mathematics, and they will be probably more useful in the future. The theorem proof, the automated theorem proving is really only beginning, and there are many ideas and much to do. The LLMs will probably not be the final tools, AI tools that will be used in mathematics, but today it's what we have. And I believe that the practice of mathematics will change, but I think that's okay. I mean, there used to be a time where computing the digits of pi was a large area of mathematics. It changed a little bit, but that's okay. And I part of the group who believe that AI will definitely not replace mathematicians, but give us more tools to do our job. All right, thank you for your attention.